All right, we are talking, we're working in section 3.5, exponential and logarithmic equations and applications. So the first objective, we want to solve exponential equations. Okay, we want to solve exponential equations. So what are exponential equations? Let's first make sure we understand what an exponential equation looks like. An exponential equation might be something that looks like 4 to the 2x minus 3 power equals 64. That's an example of an exponential equation. 4 to the 2x minus 3 power equals 64. All right. And the problem is, how do you get this variable out of the exponent, right? How do you get this variable out of the exponent? Okay. So now we know what they are. How do we solve them? Well, the first thing we're going to use is called the equivalence property. Equivalence property, they say, of exponential equations. Equivalence property of exponential equations. And I'm not going to write down all the preconditions, make sure you read it. It says that b, x, and y are real numbers with b greater than 0, b greater not equal to 1. So b greater than 0, b not equal to 1. All right. So the rule says b to the x equals b to the y. They say implies that x equals y. There's my equivalence property for exponential equations. If I've got the same base, and it's critical that b has to be the same, right? If b to the x equals b to the y, then x equals y, okay? So with that in mind, example 1, solve. Solve. So they say 3 to the 2x minus 6 equals 81. 3 to the 2x minus 6 equals 81. That's my first exponential equation I want to try to solve. 3 to the 2x minus 6 power equals 81. All right. Well, I can only use this rule if the bases are the same. This has a base of 3, but I've got to rewrite this such that it has a base of 3. Well, 81 is the same thing as 3 to the 4th power, right? 3 times 3 gives you 9. 9 times 3 gives you 27. 27 times 3 gives you 81. So 81 is the same thing as 3 to the 4th. So again, b to the x equals b to the y. So I have this exact form now, so that I can conclude that the exponents are equal. So 2x minus 6 is the same as 4. So now I'll just be solving this linear equation. I'm going to add 6 to both sides. 2x equals 10. Then I'll divide by 2. X equals 5. So there would be the solution to my equation, right? And I can check myself very easily. All I got to do is in my original equation where I had an x, put a 5. 2 times 5 is 10. 10 minus 6 is 4. 3 to the 4th is 81. You can do your calculator and check it. B. B says 25 to the 4 minus t. 25 to the 4 minus t power, okay, equals, they say 1/5 to the t plus 1. 1/5 to the 3t plus 1, yeah. 1/5 to 3t plus 1. Okay? So 25 raised to the 4 minus t power equals 1/5 to the 3t plus 1. Now again, I can only use this property when I have the exact same base. I couldn't apply that property until I had 3 to the 2x minus 6 equals 3 to the 4th. The base must be the exact same before you can apply that property. So these two things look like powers of 5, but let's be a little careful. 25 is the same thing as 5 squared, but that's raised to the 4 minus t power. And 1/5 is the same thing as 5 to the negative 1, and he's raised to the 3t plus 1 power. I've got to get that same base. I've got to write them in terms of the same base before I can apply that equivalence property. Okay? Well, now that I have 5 raised to the second power raised to that power, whenever you have an exponent raised to an exponent, you multiply. So that'll be equal to 5, 2 times 4 minus t. Same thing here, this will be equal to 5 negative 1 times 3t plus 1. Okay, whenever you have an exponent raised to an exponent, those two exponents multiply. So since I have b to the x equals b to the y, I can use that property to conclude that 2 4 minus t power is equal to negative 1, 3t plus 1. Push this through, you get 8 minus 2t equals negative 3t minus 1. You need to get everything with t on one side, so I'm going to add 2t to both sides. If I add 2t, well, let's do it this way. I want positive, so I'm going to add 3t. Add 3t there, I got to add it here. Okay, that gives me 8 plus 2t equals negative 1. Subtract 8 from both sides. Okay, subtract 8 from both sides. Okay, that'll give me 2t equals negative 9. Okay, that's 1t, I'm sorry. Negative 2t plus 3t is just 1t. Right? Negative 2t plus 3t is 1t. Then I subtracted 8, so I get t equals negative 9. That's my solution. T equals negative 9. It's perfectly fine for that to be a negative number. And you can check yourself if you want. Just like we did the first one, plug it back to the original equation and check yourself. So nothing hard about that. All right. Well, again, that property, that little equivalence property that I wrote down works really well when I can set that thing up. And again, I can't apply that property until I get to this point on this problem or this point on this problem, right? B to the x equals b to the y, then x equals y. B to the x equals b to the y, then x equals y. You have to have the exact same base to be able to apply this property. Well, the problem becomes, if I ask you to solve, they say 7 to the x equals 60. 7 to the x equals 60. Well, I've got a problem because on all of these, I could express 81 as something with an exponent with a base of 3. So I'd have the same base. Same thing here, I can express this number and this number as base 5. But there's no way for me to express 60 as a number with base 7. There is no way for me to express 60 as a number that has base 7. So I'm going to need another method. That equivalence property will not work when I can't express things with the exact same base. So, to solve these types of problems, okay, so steps to solve exponential equations. I'm going to say using logarithms. Okay? We're going to use logs to solve those type of questions. So number one, they say isolate the exponential expression on one side. Of the equation. We're going to isolate the exponential expression on one side of the equation. Okay? Step two, take a log of the same base on both sides of the equation. So take a log of the same base on both sides of the equation. Take a logarithm of the same base on both sides of the equation. Number three, use the power rule for logs. Use power rule for logs. Okay. They say to bring down the exponent for solve. We're going to see how this works. Solve. Okay. We're going to see how this works. we're going to do it without. So this is example 2. Example 2. So 7 to the x equals 60. Okay? So it says isolate the exponential expression on one side of the equation. Well, that's already done. The exponential expression is 7 to the x. It's already isolated. So take a log, and since this is a base 7, I'm going to take a log to the base 7 of 7 to the x. If I do it on one side, I'm going to do it on the same thing on the other side. Just like always, when you work with an equation, whatever you do to one side of the equation, you do the exact same thing to the other. Okay, and I've got to take a log base 7 on this side, I have to take a log base 7 on that side. Well, log base 7 of 7 to the x, the power rule for log says this is x times log base 7 of 7. Okay? This is x times log base 7 of 7. Divide both sides. Divide both sides. I'm trying to solve for x, so divide both sides by log base 7 of 7. Okay? These cancel. X is log base 7 of 60 over log base 7 of 7. Now, you always got to simplify as much as possible. We learned some log properties last time. The log base b and the log property specifically I'm talking about, log base b of b is 1. So this thing in the bottom, log base b of b, log base 7 of 7, that's just 1. So x turns out to be log base 7 of 60. That's the exact answer. Log base 7 of 60. Now, that is an accurate answer, but that's not the way the book did it. Let me do it the way the book did it. Since your calculator only knows 2 different logs. Your calculator can do log base 10 and log base e, right? Your calculator can do log base 10 or log base e. So we're going to do this same problem. We're going to use log base 10. So let's just take log of that. Log 60. And in fact, since the book does log, I'm going to do natural log. I'm going to do natural log. Okay? I'm going to use natural log. We're going to get the same answer. You're going to get the same answer. So, ln 7 to the x, that power rule for log says this becomes ln of 7, ln of 60. To solve, I divide both sides by ln of 70, or ln of 7 rather. So that x is ln of 60, ln of 7. Take your calculator, because you can do the ln of 60 and you can do the ln of 7 on your calculator. If you divide those two, that thing's going to give you 2.1071. This is the exact answer, but it's approximately 2.0, I just forgot that fast, 2.1041. Okay? So we see 2 different ways. And the reason we stay away from that is your calculator can't do log base 7. This is a correct answer. But how do you know? You can do it, get online, I guess, and use one of those log calculators. There are things available online where you can look these things up. But if we use basic log, common log, log base 10, or natural log, we'll be able to get that answer with our calculators. So that's how we're going to solve these exponential equations when we can apply that nice equivalence property that we use on example 1. So let's just do some more. Let's do example 3. I'm just going to say solve. We know how to do it now. So A says 10 to the 5 plus 2x, okay, plus 820, they say equals 49.6. 10 to the 5 plus 2x power plus 820 equals 49,600. Well, that's step 1 of the process I just erased, said that isolate the exponential term. So I'm going to get this thing by itself first. So I'm going to subtract 820 first. Okay? That gives me 10 to the 5 plus 2x power 49,600 minus 820, well, that is 48,780. Okay? So I've isolated the log term. So the next thing to do is take the log of both sides. I'm going to take a common logarithm because of what we just talked about. If I take a common log on that side, I got to take a common log on this side. Okay? Well, log to the base 10 to the power, that power comes down by the power rule, right? That's still there. Okay? And then I can divide both sides. I'm trying to solve, and the other thing about it though, log base 10 of 10, because of that same property I wrote down a minute ago, that's 1. That's one of the properties of logs. So log base 10 of 10, this is just 1. So really all I got here is 5 plus 2x equals log 48,780. Subtract 5 from both sides. 2x equals log, 48,775. And then divide both sides by 2. Okay? Divide both sides by 2. Oh, I'm sorry, I can't subtract those. 48,780. All I can do is write it like that. Okay? I can't subtract those because they're taking the log of 48,780. So I can't subtract 5 from that. That 48,780 is tied up as the argument of the log. So I cannot subtract 5 from 48,780. That was wrong. So x equals log 48,780 minus 5 all over 2. There's your exact answer. That's your exact answer. Okay? Well, B, they say solve. 2,000 equals. They say 18,000 E raised to the negative 0.4 t power. Negative 0.4 t power. I want to solve that equation. Well, the first step is to isolate the exponential term. So I'm going to divide both sides by 18,000. Okay? If you do that, you'll get 1/9. 2,000 divided by 18,000 is 1/9. Equals e to the negative 0.4 t power. Now, my base is e, so this time I'm going to take the natural log of both sides. Okay? When I do that, I'll get ln of 1/9 equals, that exponent comes down. Okay? Now, take your calculator. Take your calculator. ln of e, that's 1. So I'm going to use that fact, and again, you're going to have to learn how to simplify these log expressions. The ln of e is 1. So I get ln of 1/9 equals negative 0.4 t. The last step to solve for t is to divide by negative 0.4, and I'm going to turn it around. There's your exact answer. Okay, there's your exact answer. And I can use, I can use my rules. I forgot I can use my rules. ln of the fraction, it would be ln of 1 minus ln of 9 over negative 0.4. That's the quotient rule, right? ln of the quotient is the difference of the ln's, right? Now ln of 1 is 0. So you just get negative. This goes away, that's 0. Take your calculator and check it. Take the ln of 1, that's 0. So I just get negative ln of 9 over negative 0.4. Well, that would be ln of 9. The negative divides out, because a negative over a negative makes a positive. So there's my final answer. So I've got to apply all those rules that I can. I've got to apply all the rules that I can and simplify this thing as much as I can. Okay, now again, if you see your base is E, you will take the natural log of both sides. If the base is not E, you're going to take the common log of both sides. That's going to be our general rule. To solve these exponential equations, we'll take the common log of both sides if that base is not 10. We'll take the natural log of both sides if the base is E. Okay, example 4. Solve, and this kind of discounts what I just said. Let's do it anyway. 4 to the 2x minus 7 equals 5 to the 3x plus 1. Okay? Well, I said we take the log of both sides, and you can. You can either take the log or the natural log. It really does not matter. You have an option. You can take the log of both sides or the natural log of both sides. Okay? We're going to do, I'll do it the way the book did it. We'll take the natural log of both sides. Okay? Well, the exponent comes down. Exponent comes down. Okay? Let's go ahead and distribute. I'll get 2x L into 4 minus 7 L into 4 equals 3x times L into 5 is 3x L into 5 plus L into 5. Well, we're solving for x, so we got to get all the terms with x on both sides. So I'm going to subtract 3x L into 5 from both sides. And I'm going to add 7L into 4 to both sides. Okay? I didn't write it down, but what I did was I subtracted this term from both sides. Subtract 3xL into 5 on this side, it goes away. I'll see it over here. Add 7L into 4 to both sides. This one will go away, and I'll see it added over there. So we subtracted 3xL into 5 from both sides, and we added 7L into 4 to both sides. But that gives me all the terms with x on one side, and then all the terms that don't have an x on the other side. Now I can factor out that x. Okay? And I'll just divide by what I don't want. Do it over there, I gotta do it over here. And so x, 7L into 4 plus L into 5 divided by 2L into 4 minus L into 5. Okay? They have a 3. Oh yeah, this was a 3 L into 5. 3x L into 5. So, is that right? Yeah, I subtracted 3x L into 5 from both sides. I get that. Then I factored out yeah, so this should be minus, sorry. So then I took it, I factored out the x, so I should get minus 3 L into 5. So I should be dividing by 3, 3, 3. Now it's correct. Now it's correct. Okay. Well, what about example 5? What about example 5? So there's a lot to keep in mind. I've got to remember all those log properties, and I've got to add in all these new ones. Solve. This time they give me e to the 2x plus 5e to the x. Okay. Minus 36 equals 0. E to the 2x plus 5e to the x minus 36 equals 0. Well, that thing thing looks kind of quadratic. It looks kind of quadratic, okay? So let's do the following. Let's use a substitution. Let's say let, and I don't care what you call it, let's say u. Let u be equal to e to the x. Okay, u is e to the x. Then e to the 2x becomes u squared. 5e to the x, since e to the x is u, becomes 5u minus 36 equals 0. And now with that substitution, it definitely looks quadratic. I know how to solve these quadratic things. I can factor if I can. If I can't factor, I can use quadratic formula. So a u and a u. To get a minus 36, maybe a 9 and a 4. That better be positive, that better be negative. So there's my factorization. So now I got a product equal to 0, so either the first factor equals 0, or the second factor equals 0. Subtract 9, u equals negative 9. Add 4, u equals 4. Now go back to your substitution. U is the same thing as e to the x. So e to the x equals negative 9. Okay? Or e to the x equals 4. Okay? And to solve this, now I'm going to take the ln of both sides. Okay? But the ln of e to the x becomes x ln of e. I still got ln of negative 9. Right? Still got ln of negative 9. Right? But I've got a problem because right here I could have stopped. E to the x is negative 9. Again, I've got to remember that for the exponential function, okay? For the exponential function, you can't take the ln of negative 9. So when I go from here to here and try to take the ln of 9, I can't do it. So that means that I won't get any solutions from that side. Because that step leads to the fact that the ln of, you have to get the ln of negative 9 in the next step. You can't take the log of a negative number. Try it on your calculator. Take the ln of negative 9. You're going to get an error or a domain error. So there aren't any solutions that come from that part. That's what that tells you. So all I have really is this part. So I'm going to take the ln of both sides. Okay. Well, the ln of e to the x comes in front. Okay. And I think I mentioned this. But the ln of e, take your calculator. The ln of e is 1. Take your calculator and check it. The ln of e is 1. So the solution to that equation is the ln of 4. Okay, the solution to that equation will be the ln of 4. Okay. Well, that's how we solve exponential equations. So now we want to solve logarithmic equations. So objective 2. Objective 2, solve logarithmic equation. And just like we had that nice equivalence property, that was the first way we learned how to solve exponential equations, there's an equivalence property for logarithmic equations. So log to the base b of x equals log to the base b of y. So equivalence property for logs. And again, read the preconditions. So I'm not going to write them all down. Read it. So basically, log to the base b of x equals log to the base b of y. It implies that x equals y. That's the equivalence property for logs. So it kind of mirrors the equivalence property for exponential functions. But this one is for logs. If the log to the base b of x is equal to the log to the base b of y, then the x must be equal to the y. That makes perfect sense. And again, those bases have to be the same though. Log to the base b of x, log to the base b of y. If they're equal, then x equals y. So let's use that. Example 6, solve. Solve. They say log to the base 2. Log to the base 2 of 3x minus 4 equals log to the base 2 of x plus 2 So I have exactly that property, or that premise. Log to the base b of x equals log to the base b of y. So I can conclude that 3x minus 4 is equal to x plus 2. And now all I got to do is solve this nice linear equation. I'm going to subtract x on both sides. 2x minus 4 equals 2. Add 4 to both sides. 2x equals 6. X equals 3. Okay? X equals 3. Now, log equations, exponential equations, if you did your math right, the solution will always be good for an exponential equation. Okay, if you did your math right. With log equations, so with log equations, you must check your solution. Okay? You must check all your solutions. It wasn't as critical with exponential equations. But with a log equation, you better check your solution. Okay? So let's do that. Let's check it. I got x equals 3, so where I had an x, I should get a 3. So log to the base 2 of 3 times 3, that's 9 minus 4. Is that equal to log to the base 2, put that 3 where the x was, of 5? Well, 9 minus 4 is 5, so yes. So it checks out, okay? But again, this is critical. With log equations, you must check your solution. Because log equations were more restricted. The domain of a log equation was only positive quantities, so you better make sure that your answer, when you get your answer, you're never trying to take the log of something that's negative or something that's 0. If you are, it's not going to work. Example 7, solve. Solve. Ln of x minus 4. Okay. Equals ln of x plus 6 minus ln of x. So the ln of x minus 4 equals ln of x plus 6 minus ln of x. Okay. Well, the property says that log to the base b of x, whenever that's equal to log to the base b of y, then x equals y. That was there's my little equivalence property. If the log to the base b of x equals log to the base b of y, then x equals y. Well, I can't use that property when I have two logs, so I'm going to have to use my log properties to combine this. This is subtraction, so I can rewrite that as x plus 6 over x. Because the log of the quotient is the difference of the logs. So I can't apply that property until I have a single log with the same base here of something equals a single log to the same base here of something. I can't apply that property when I have two logs. So the first thing I do is apply my quotient rule for logs to rewrite these two logs as a single log. Now, this thing looks like this thing, and now I can apply that property. So since ln log to the base c of b, log to the base c of x minus 4 equals log to the base c of this, then I can conclude that x minus 4 better be x plus 6 over x. Multiply both sides by x. Distribute. Get the x on the other side. And subtract the 6 from both sides. Right? Equals 0. I can factor this dude. X and x minus 2 minus 3 equals 0. Okay? So either x minus 2 equals 0, or x minus 3 equals 0, x equals 2 is one solution, x equals 3 is another solution. Okay? And again, all you really have to do is look at this original equation, put these numbers back, and just make sure you're not trying to take the log of 0 or the log of a negative quantity. So when I put a 2 minus 4, so we're checking it. We're checking it. X equals 2 is the first one. Put the 2 in, ln of 2 minus 4. I can stop right there because 2 minus 4 is ln of negative 2. 2 minus 4 would be ln of negative 2. I can't do that, so that solution is no good. If that solution results in you trying to take the log of something negative or the log of 0, then that solution is no good. Okay? Well, I did this wrong. I did this wrong. Let me show you. My factorization is wrong. X times x is x squared. The outer product would be negative 3. The inner product is negative 2. That's negative 5x. But a negative times a negative would make a positive 6 and not a negative 6. So my factorization was wrong. So I should have had minus 6 plus 1. Now the factorization is correct. I'm sorry. I should have had x minus 6 and x plus 1. So now either x equals 6 or x equals negative 1. Those are my two potential solutions. So let's check them. So let's check x equals negative 1 first. Put a negative 1 here. So ln of negative 1 minus 4. I can stop right there because that's ln of negative 5. I can't do that. So negative 1 is no good. When you put it right here, I don't care what happens over there. The moment you see ln of something negative, you can stop because it's over. You can't take the log of something negative. You can't take the log of 0. 6, if you check a 6, so x equals 6, you'd have ln of 6 minus 4, 4. And the question is that equal to ln of, put a 6 here, so that would be ln of 12 minus ln of 6. Well, that's fine, because you never tried to take the log of a negative. So is that equal to this? ln. So ln of 12 minus 6, the quotient rule says this is ln of 12 over 6. But that's ln of 2, that's ln of 2, that's a good solution. So there's a good solution, x equals 6. X equals negative 1 is no good. Okay? All right. So nothing hard about this. Nothing hard about this. So the next thing they talk about is solving log equations. Okay? By using exponential form. By using exponential form. Okay? Because we'll still have problems. Okay? Because that equivalence thing will not always work. Okay? That equivalence thing will not always work. Because sometimes you're going to have log terms and constant terms. So they give us one more method. It's called solving log equations by using the exponential form. So step 1, they say given a log equation, isolate the logs on one side of the equation. So isolate logs on one side of the equation. And this is on page 412. Page 412. Step 2. They say use property of logs to write the equation in the form. Use log properties to write equation in the form. They say, well, log to the base b, x equals y. Okay? Log to the base b, like they call it k. Wouldn't matter, they call it k. Where k is a constant. Okay? Step 3, write equation in exponential form. So we're going to swap from log form to exponential form. Write the equation in exponential form. Solve the equation. I'm just going to say solve. And we'll see what this means in practice in just a moment. And then number 5, check. Check your solution. So make sure you read this. I'm paraphrasing a lot of this. Make sure you read it on that page 412. And let's just do some following that model. Okay. All right. So example 8. Example 8. Solve. So they say 4 log to the base 3, 2t minus 7. 4 log to the base 3, 2t minus 7 equals 8. 4 to the log base 3, 2t minus 7 equals 8. Okay? So step 1, isolate logs on one side. So I don't want 4 times the log of this. I want just the log term. So the first thing I'm going to do is divide by 4 to get rid of the 4. So now I get log to the base 3, 2t minus 7 equals 2. Okay? Log to the base b, 2t minus 7 equals 2. Okay? So now they say use log properties, write the equation in the form log to the base b of x equals k. Well, we've done that. We've got exactly this form. Log to the base 3, 2t minus 7 equals k. K is a 2. The x is being represented by 2t minus 7. Now they say go from exponential to log form. Well, that's that y equals log to the base b of x is equivalent to b to the y equals x. That's what they're talking about. When we first started talking about these logs, we said that that was my equivalent. So log to the base b of x equals y. This is log form. I want to rewrite it in exponential form. Log to the base b of x equals y. So my base b to the y power 2 is equal to x. So if I convert from log to exponential form, that's what I'll get. Okay? If I convert from log to exponential form using that rule up there, which we have to know by now, that's what I get. Well, 3 squared, 3 to the second power is just 9. Add 7 to both sides. Divide by 2, and I'm going to turn it around. T is 8. T is 8. Well, let's check it. The last step says check it. So, I had 4 log to the base 3, 2t minus 7, and it was equal to 8. So I'm checking t equals 8. Everywhere I had t, I'm going to put an 8. 2 times 8 would be 16 minus 7. And we're going to see if we get 8. Well, that makes 4 log to the base 3. 16 minus 7 is 9. Right? But 9 is the same thing. 9 is the same thing as 3 squared. But log to the base 3 of 3 squared is 2. That's one of those log properties. And that's 8. So you get 8. That is a good solution. That is a good solution. So that's how we're going to do these problems. Let's do another one. Step 9, solve. Solve. Log of w, excuse me, log of w plus 47 equals 2.6. Log w plus 47 is 2.6. Log of w plus 47 equals 2.6. So I've already got log form. I've got log to the base 10 of this equals, so log to the base b of x equals y. So I want to convert, because I can jump down to this step right here, or right here. I'm going to write my equation in equivalent exponential form. So my base b, if I don't see the base is 10. So my base b to the 2.6 power, the y power, is equal to w plus 47. Subtract 47 from both sides. W equals 10 to the 2.6 power minus 47. Okay? That's the exact answer. They say that's approximately 351.1072. There's the approximation. There's the exact answer. Okay? If you check it, it works. If you check it, it works. Okay? All right. Let's see. Let's do another one. This is example. Example 2. Solve log to the base 2 of x equals 3 minus log to the base 2 of x minus 2. Okay? Well, I got to isolate one log on one side. That was my first rule. So I'm going to add log to the base 2 of x minus 2 to both sides. I'm going to add. I did add log base 2 of this on this side. I added log base 2 of this on that side. And I got this, okay? I see the sum, so I can use the product rule for logs to rewrite this as x times. X minus 2 is that. Product rule for logs. The log of the product is the sum of the logs, okay? Well, now I've got that log form. Log to the base b of x equals y. So all of this stuff is being represented as x. I know it's a little confusing with variables, but variables are placeholders. That's all they are. It's not literally meaning it has to be x. It means just whatever's there. Log to the base b of what's there x equals what's there y. So convert this to exponential form, and you'll get the base raised to the third power is equal to x. Okay? So there's my corresponding exponential form. 2 cubed is 8. This will give me x squared minus 2x. And subtract 8 from both sides, rather. And now I'm going to turn it around. With that, okay? Can you factor it? X and x. Let's see. How about a 4 and a 2 minus plus? Negative 2x, negative. Yeah, that works. That works. So, my two solutions, x minus 4 equals 0 means that x equals 4. X plus 2 equals 0 means that x is negative 2. We've got to check these solutions. And again, all you're really checking is that these solutions, when you plug them in that original equation, don't yield the log of a negative quantity or the log of 0. Okay? So if I put x equals negative 2 right here, I have log to the base 2 of negative 2. So that solution is no good. If I put a negative 2 in this first term to check it, log to the base 2 of negative 2, I can't take the log of a negative. That solution is garbage. So the only possibility now is 4. So put the 4 there. Log to the base 2 of 4. Is that equal to 3 minus log to the base 2 of 4 minus 2? Well, that's log to the base 2 of 4. Is that equal to 3 minus log to the base 2 of 2? Okay? And yeah, it's going to work. It's going to work. Because this is log 4 is the same thing as 2 squared. Log to the base b of b to the x is just x. So I just get 2 here. Let's work on this one. 3 minus. Log to the base 2 of 2. Log to the base b of b is 1. 3 minus 1 is 2. So it works. Just using all those log properties. Okay. Let's see. That's fine. The next one they do is example 11. I'm going to let you do that. I'll do example 12. That'll be our last example. Example 12. So they say, suppose the sound at a rock concert is 124 decibels. Suppose the sound at a concert is 124 decibels. Okay, decibels, dB. They say use the formula. Use the formula. They say L equals 10 log I over I 0. They say where I is the intensity of sound, I is the intensity of sound, and they give you units, and L represents the loudness of sound. Okay? And they give you, now all this means is the intensity at time 0. That's what I sub 0 means. I is intensity, so I sub 0 means the intensity at time 0. So what was the initial intensity? So I sub 0 is 10 to the negative 12. And they give you the units, I don't care. So, let's use that formula to find the intensity. So L is 10 log of, and this is L, by the way, they told you what L was. So replace L. L is 124 equals 10 log of I over I. So I know that, give me that. That's 10 to the negative 12. So replacing what I know, you get that. Again, read the problem and you'll get a little more context. Read the problem, it's on page 415. All right. So I've got to solve that equation for I. They want me to find I. Okay. So the first thing we do, is we isolate the log. So I'll divide both sides by 10. By 10 there, got to divide by 10 there. I get 12.4. 124 divided by 10 is 12.4. All I got left over here is log I over 10 to the negative 12. Okay? So there's my log form. I'm going to rewrite that using exponential form. Okay? So, log to the base b of x equals y. Log to the base 10 of x equals y. So b, my base, raised to the y power is equal to x. That's my corresponding exponential form. So to solve that, I multiply both sides by 10 to the 12, and I'm going to turn it around. So I have 10 to the 12.4 times 10 to the negative 12. Again, multiply this side by 10 to the negative 12, this side by 10 to the negative 12. When I multiply, I add exponents. I'm multiplying something with the same base. You add exponents, so you'll get 10 to the 0.4. Okay? 10 to the 0.4, they say, is 2.5. I is 2.5. And they give you the units, but I'm not worried about it. So that's the intensity of the sound. Okay? And they give you a part B, but it's pretty straightforward. So this concludes this section. If you have any questions, please let me know.